Today, we will discuss about unsymmetrical fault analysis. In the previous module of symmetrical components, we had discussed about in detail what we mean by symmetrical components, what are the uses of these symmetrical components, where are we going to use symmetrical components, and how to represent the various power system components with respect to their symmetrical impedances and symmetrical networks, and hence obtain the symmetrical networks for a general power system that is provided. Using these concepts, let us try to identify how to do the fault analysis on unsymmetrical faults. Whenever the system is undergoing unsymmetrical fault, the system will also be unsymmetrical in nature. Initially, the system is symmetrical physically, and all the currents and the voltages that are present in the system will be totally balanced. Now, because of an unsymmetrical fault occurring in the system will become unbalanced and it will step out of symmetry. When this happens, the general analysis of fault cannot be done on the power system. Hence, we use the concept of symmetrical components, symmetrical impedance, and symmetrical networks to do the analysis of unsymmetrical faults on the given power system. So let's talk about what are the different types of the faults. How are each of these faults analyzed in case of an electrical power system? There are various types of faults that occur on the power system. The unsymmetrical faults are basically categorized into two types: the shunt type of faults, which leads to the short circuit, and the series types of fault, which leads to the open circuit. Shunt types of faults. In shunt types of faults, depending upon how this fault is occurring and how many lines are affected, we are having various categories of shunt types of faults. The shunt type of faults involves the short circuit of the conductors between the conductors or between the conductors and the ground. They are characterized by the increase in the current, that will be a huge, large increase in current, and fall in the voltage because of the short circuit. And the frequency will also fall down in the faulted phase. Shunt type of faults are classified as single line to ground fault, second line to line fault, and the third double line to ground fault. Next is the second category of faults, which is called as the series types of fault. In series types of fault, one or two lines in the three-phase system gets opened while the other lines remain intact. Such faults are called as the series types of faults. They are characterized by increase in voltage and frequency and fall in current because of the open circuit. Series type of faults can be grouped as one conductor open fault or two conductor open fault. Relatively, when these types of faults are organized in the order of their occurrence and in the order of their severity, then the types of faults can be arranged in the following way. Symmetrical faults, which we had studied in module 2, is the most severe type of the fault, but its occurrence is the rarest in the power system. It contributes to only 5% of the faults. Double line to ground fault is the second most severest fault, which occurrence is up around to 10%. Double line faults is at 15% occurrence, and single line to ground fault is the most occurring fault on the power system, which contributes for 70% of the faults. So these faults, whatever has been listed here, starting from symmetrical faults to single line to ground fault, is arranged such a way that it is in the increasing order of its occurrence. And when it comes to the severity, symmetrical faults is the most severe and single line to ground fault is the least severe fault. Now let's quickly move on to the fault calculations in the most of the generally occurring components in the power system. We will be concentrating on synchronous generator, and power system in general. First, look at the fault calculations in synchronous generators. As told earlier, we are talking about a system and its components which is balanced, symmetrical in nature under the normal operating condition. Only when an unsymmetrical fault is occurring on these components or on the power system, then the system beyond that particular point after the fault has occurred will be no more balanced. They will step out of symmetry and will become unbalanced. So we are considering a balanced three-phase synchronous generator which is subjected to unsymmetrical fault at its terminals. So the diagram represents a three-phase synchronous generator. F is the point of fault which is beyond the synchronous generator at its terminals. Otherwise, if the fault is not there on the system, this part represents the balanced three-phase generator which is having an impedance Z in each of its phases and an EMF induced EA, EB and EC in its phases A, B and C respectively, such that the magnitude of EA, EB, EC are all equal to one another and they are 120 degrees with respect to one another. So this is the balanced three-phase generator at which the terminals of which the fault F is occurring. The fault is unsymmetrical and hence to the left of the fault point the alternator is completely symmetrical. In such a system, currents of the given sequence produce voltage drop of the same sequence only. The sequence impedances which offer for the flow of these currents are also uncoupled in nature. Let's see how this can be shown. Since it generates balanced voltages, only positive sequence voltages will be present. The following equations, whatever we are going to discuss now, are applicable to a synchronous generator even during an unsymmetrical fault, because to the left of the fault the system is still symmetrical in nature. VA1 equal to EA minus IA1 Z1, VA2 equal to minus IA2 Z2, VA0 equal to minus IA0 Z0. These equations are called the system equations. The single phase representation of the positive sequence network of the synchronous generator consists of positive sequence generated EMF in series with a positive sequence impedance Z1 through which the positive sequence current IA1 flows. The single phase representation of the negative sequence network consists of negative sequence impedance Z2, no negative sequence voltage is generated. The single phase representation of zero sequence network consists of zero sequence impedance Z0 with no zero sequence generated voltage. Single line to ground fault on unloaded generator. The following diagram represents the condition when a single line to ground fault, LG fault, is occurring on an unloaded star connected generator with its neutral grounded through a reactance as shown in the figure, and this neutral reactance is Zn. Z, Z and Z are the balanced impedances in all the three phases A, B and C of a balanced unloaded synchronous generator, and at its terminals, especially in only one phase A at point F, the fault has occurred, and the fault has occurred because that particular point F is now grounded. So let's see how this affects the performance of the system. So from the diagram, you can see that the current here now IA is nothing but the current that flows to the ground, which is the fault current. Because the system is unloaded, it is open, IB and IC will be equal to 0. So IB is 0, IC is 0. At point F, A gets grounded. Therefore, the voltage will become equal to 0, totally shorted to the ground. So, voltage will become equal to 0. These are referred to as the terminal conditions of the given power system. Next, from these three terminal conditions that are specified in terms of line currents and phase voltage can now be transformed into symmetrical components because they are not now balanced. If they would have been balanced, all the three currents would have been the same, all the three voltages would have been the same and will be displaced by 120 degrees. But now, because there is a change in the value of the currents and the voltages, the system represents an unbalanced system. Therefore, this condition can now be represented in terms of symmetrical components. We know that the current IA0, the zero sequence component of the line current, will be equal to 1 by 3 times of IA plus IB plus IC. IB and IC values are known, which is given as 0 and 0 from the terminal conditions. Therefore, IA0 is equal to 1 by 3 times of IA. Similarly, the positive sequence current IA1 is 1 by 3 times of IA plus alpha IB plus alpha square IC, which is 1 by 3 times of IA, IB and IC is 0. Therefore, it comes out to be 1 by 3 times of IA. Similarly, IA2 will also be equal to 1 by 3 times of IA. So, from the above three expressions, we can make out that the positive sequence current IA1 is same as the negative sequence current IA2 is same as the zero sequence current IA0, and all these three values are now equal to 1 by 3 times of IA. That means to say same amount of current is flowing in positive sequence network, in negative sequence network and zero sequence network. The terminal conditions VA equal to 0 indicates that VA0 plus VA1 plus VA2 equal to 0. What is VA? VA is equal to VA0 plus VA1 plus VA2, and now that value equal to 0. So from these symmetrical component expressions what we have obtained, we can observe that since all the three currents are the same in all the three networks of positive, negative and zero sequence, it indicates that all these three networks are connected in series. Therefore, from the above expressions, we will write the representation of the sequence network of the single line to ground fault occurring in the system. So, the positive sequence network, where we have the positive sequence impedance in series with the induced EMF. Current flowing is IA1. Second, the zero sequence network having the impedance, zero sequence impedance Z2. Currents flowing IA2. And the zero sequence network having the value Z0, the zero sequence impedance, which is made up of the zero sequence impedance of the generator and 3 times the neutral reactance put together the zero sequence impedance through which the current IA0 flows. So this is positive sequence network, negative sequence network, zero sequence network of the given synchronous generator. Now from the expressions of the symmetrical components, we have found that IA1 is equal to IA2 equal to IA0. So they have to be connected in series such that the same current flows. So all the three networks are now connected in series to allow for the same amount of current to flow through all the three networks. VA1, VA2 and VA0 represent the drop in the positive sequence network, negative sequence network and zero sequence network respectively. Now, after having drawn the representation of the fault in terms of symmetrical fault components in the circuit diagram, we can obtain the expressions from these circuit diagram. The following relations can be obtained. IA1 is equal to IA2 is equal to IA0, that is equal to EA, the induced EMF, the only voltage source, divided by Z1 plus Z2 plus Z0. It has to cater for all the three impedances. The voltage VA1, that is the positive sequence network voltage, is equal to EA1 minus IA1 Z1. EA1 is the only source of voltage, so that is equal to EA minus EA by Z1 plus Z2 plus Z0, substituting for IA1 into Z1. That is EA into Z2 plus Z0 divided by Z1 plus Z2 plus Z0. VA2, that is the drop in the negative sequence network, is equal to minus IA2 Z2, that is minus EA Z2 by Z1 plus Z2 plus Z0, and VA0 minus IA0 Z0 is equal to minus EA into Z0 by Z1 plus Z2 plus Z0. So these are the relations that can be obtained for the sequence currents and the sequence voltages, from which we can obtain the expression for the fault current. The fault current IF, as seen in the first diagram corresponding to the single line to ground fault, is nothing but equal to the line current IA. Therefore, IF equal to IA, but we know IA equal to IA0 plus IA1 plus IA2. Now all the three are equal to 1 by 3 times of IA. Therefore, IA is equal to 3 times of IA0. Since IA0 is equal to 1 by 3 IA, this expression we had seen. Therefore, IF equal to IA, which is equal to 3 times of IA0. So, substituting for IA0 here, we have IF to be equal to 3 times EA by Z1 plus Z2 plus Z0. Now, in this Z0, we had considered as equal to the total impedance of the zero sequence of the generator and 3 times the neutral reactance that will be connected. Now, there may be cases where the generator is not at all grounded, the neutral point is isolated. In that case, the Zn value will become infinity. Therefore, the Z0 value will also become infinity, representing open circuit. In that case, there is no chance for the fault current to flow in the circuit. Other case may be, it is not grounded through any reactance, but it is solidly grounded. Okay. Then the value of Zn will be equal to 0. Then the value of Z0 will be simply equal to the value of Zg naught. But there is a scope for the fault current to flow. That means to say, whenever the system is ungrounded, whenever the synchronous generator neutral point is ungrounded, there is no possibility of fault current to flow through the circuit. Now, in this previous case, we had talked about the single line to ground fault in the system. Now, in the path of this ground occurring between the phase A and the ground, if a fault impedance is included, what will be the changes in the representation of the circuit and the expressions of the symmetrical components and the fault current is now seen. The single line to ground fault and unloaded generator through the fault impedance. The circuit diagram is represented. So earlier case, from the point F it was directly grounded, but now there is a fault impedance that is coming into picture. Otherwise, all other remaining parts are same as in the previous case. So the terminal conditions now changes. The current IB and IC still continue to be 0, but the voltage at the point of fault will now not be equal to 0, but will be equal to drop in the fault impedance IA into ZF. Further, IA is nothing but equal to the fault current IF. Now from these terminal conditions, we can write the expressions for the symmetrical components of currents and voltages. IA naught is 1 by 3 times of IA plus IB plus IC. IB, IC continue to be 0, therefore IA naught is 1 by 3 times of IA. Similarly, IA1 will be 1 by 3 times of IA and IA2 will be 1 by 3 times of IA, indicating that IA naught equal to IA1 now equal to IA2 and all the values are equal to 1 by 3 times of IA, which still indicates that the positive sequence network, negative sequence network and the zero sequence network are still connected in series. Coming to the voltage expression, we have VA to be equal to IA into ZF, but VA is equal to VA0 plus VA1 plus VA2 and IA is nothing but equal to 3 times of IA0. IA0 is 1 by 3 times of IA, therefore IA is equal to 3 times of IA0. So substituting here, we have 3 times of IA0 ZF, therefore VA0 plus VA1 plus VA2 is equal to 3 times of IA0 into ZF. What is this VA0? Drop in the zero sequence network, drop in the positive sequence network, drop in the voltage across the negative sequence network. All these three together is 3 times IA0 ZF. This indicates that the current that is flowing through the three networks now will flow through an impedance ZF, which is having a magnitude 3 times of ZF. Will flow through an impedance which is having a magnitude 3 times of ZF. It can be observed that all the sequence currents are equal and the sum of the sequence voltages is 3 IA0 ZF. Therefore, these equations suggest a series connection of network through a series impedance 3 times ZF. Therefore, the circuit is now represented as the same current flows through all three networks and finally returns back through 3 times ZF. Okay. So from this circuit, now we can write the expression for the fault. IA0 equal to IA1 equal to IA2, which is obtained as the only voltage source divided by all the impedances in the circuit, Z1 plus Z2 plus Z0 plus 3 ZF. VA1 is equal to EA minus IA1 Z1. Substitute for IA1 from the previous expression. So EA into Z2 plus Z0 plus 3 ZF divided by Z1 plus Z2 plus Z0 plus 3 ZF. VA2 is minus IA2 Z2. Substitute for IA2. Therefore, VA2 is minus EA Z2 by Z1 plus Z2 plus Z0 plus 3 ZF. VA0 is minus EA Z0 by Z1 plus Z2 plus Z0 plus 3 ZF. The fault current IF is nothing but the current in the line A, IA, which is equal to 3 times of IA naught. So substituting for IA naught here, we have 3 times EA by Z1 plus Z2 plus Z0 plus 3 ZF. Now, in this expression of the fault current, if the condition is such that the unloaded generator star point is not connected to the ground, if it is isolated, then it represents an open circuit at that point. So Zn becomes infinity, then Z0 will also become infinity. Therefore, the current IF will become equal to 0. It means that if the neutral is left ungrounded, if it is isolated, then there is no scope for the fault current to flow through the circuit. Now let's move on to the analysis of the next type of fault on the synchronous generator. Line-to-line fault on unloaded generator. The below circuit represents a line-to-line fault which is occurring between the lines B and C. So IB and IC are such that they are mutually opposite in direction, which indicates IB equal to minus IC or IC equal to minus IB. Since the generator is unloaded, the current IA is equal to 0 because it is just kept open. The fault current is nothing but equal to IB or equal to minus IC. And the voltage here, that is the voltage VA, VB and VC are such that VB is equal to VC because they are at the same point now, they are shorted together. Now, from these terminal conditions, we can obtain the symmetrical component expressions. IA naught is 1 by 3 times of IA plus IB plus IC. IA is 0. IB plus IC is also 0 because IC is opposite of IB or IB is opposite of IC. Therefore, IA naught is equal to 0. IA1 is 1 by 3 times of IA plus alpha IB plus alpha square IC. IA is 0. Alpha IB minus alpha square IB because IC is equal to minus IB. So taking common out the value of IB, we get IA1 to be equal to 1 by 3 times of alpha minus alpha square IB. Similarly, IA2, we get it to be 1 by 3 times of alpha square minus alpha IB. So again here it indicates that IA1 is minus IA2 or IA2 is minus IA1. They are opposite mutually in opposite directions. VA naught is minus IA naught Z naught because IA naught is 0, VA naught is also 0. VA1 is 1 by 3 VA plus alpha VB plus alpha square VC. That is 1 by 3 VA plus alpha plus alpha square VB because VB is equal to VC. Therefore, VA1 is equal to 1 by 3 times of VA minus VB because 1 plus alpha square equal to 0, which indicates that alpha plus alpha square equal to minus 1. So here in place of alpha plus alpha square we have substituted for minus 1. So VA1 is equal to 1 by 3 times of VA minus VB. VA2 on similar lines will be equal to 1 by 3 times of VA minus VB. So from the above expressions we can see that VA1 is equal to VA2, that is the positive sequence voltage is equal to the negative sequence voltage. The voltages are equal only when the circuits are in parallel. Therefore, the positive sequence network is parallel to the negative sequence network. Whereas IA naught is also 0, VA naught is also 0, which indicates that there is no load on this part of the circuit. Also, it is shorted on itself. So it is isolated and shorted on itself. So the above equations suggest that the positive sequence network and the negative sequence network has to be connected in parallel to one another. and the zero sequence network has to be separated and shorted on itself. Also, it is shown that IA1 is equal to minus IA2 or IA2 is equal to minus IA1. That means to say the current that is flowing are in direct opposition to each other. From this diagram now, we can obtain the expression for IA1 which is equal to minus IA2 as EA by Z1 plus Z2. IA0, VA0 equal to 0. VA1 is same as VA2, it will be equal to EA minus IA1 Z1, and substituting for IA1 we get VA1 to be equal to EA Z2 by Z1 plus Z2. From these expressions we can obtain the fault current IF. IF as seen from the diagram is same as IB or IC. Therefore, IF is IA0 plus alpha square IA1 plus alpha IA2. IA0 is 0. IA1 is alpha square minus alpha IA1 because IA1 is equal to minus IA2, substituting that. So alpha square IA1 minus alpha IA1. So alpha square minus alpha is taken common out, IA1. Alpha square minus alpha is equal to minus j root 3 IA1. Therefore, the fault current IF is minus j root 3 IA1. The magnitude alone of fault current is important to us. Therefore, IF magnitude is root 3 times of IA1. And IA1 is EA by Z1 plus Z. So substituting, we have IF to be equal to EA by Z1 plus Z. In this case, if the neutral is not grounded, it does not affect anything on the fault current because the fault current expression is not having the value of Z0. Hence, the fault current is independent of the value of Z0. The presence or the absence of the neutral, grounded or ungrounded, does not affect the flow of fault current in case of LL fault. Now, if the same LL fault occurs through a fault impedance ZF, so instead of B and C directly being shorted, if it is shorted through a fault impedance, how does the analysis change? IA still continues to be 0, but now IB plus IC equal to 0. IC is opposite of minus IB. VB is now not equal to VC but is equal to VC plus IB into ZF, the drop there in the fault impedance. From the above equations, we can obtain the symmetrical component expressions for the current IA0, which is 0. IA1 continues to be the same, 1 by 3 times of alpha minus alpha square IB. IA2 is also same, 1 by 3 times of alpha square minus alpha IAB, which indicates that IA2 is equal to minus IA1. Next, coming to the voltage, VA0 is minus IA0 Z0. Since IA0 is 0, VA0 is 0. VA1 is 1 by 3 times of VA plus alpha VB plus alpha square VC. And VA2 is 1 by 3 times of VA plus alpha square VB plus alpha VC. Therefore, if you take the difference of these two, VA1 minus VA2, we have 1 by 3 times of alpha minus alpha square VB plus alpha square minus alpha VC. But VB minus VC is IB into ZF. VB minus VC is IB into ZF. So representing like that, alpha minus alpha square VB. Change, take out this minus out. So this becomes alpha minus alpha square VC with a minus sign here. Therefore, alpha minus alpha square, if you take common out, you have VB minus VC. And VB minus VC is IB times of ZF. Therefore, VA1 minus VA2 is IA1 ZF. So from this equations of symmetrical components of currents and voltages, we can find that VA1 equal to VA2 plus IA1 ZF. VA1 equal to VA2 plus IA1 ZF, and the connection is such that IA1 is in opposite to direction of IA2. VA1 and VA2 are such that VA1 is equal to VA2 plus IA2 ZF or minus IA1 ZF. Therefore, between the positive sequence network and the negative sequence network, now we are having a impedance ZF coming into picture. Whereas IA0 is 0, VA0 is 0, which indicates the zero sequence network is totally isolated and separated. From the above diagram, we can write the expressions for the current IA1, which is in direction opposite to IA2 minus IA2, as EA by Z1 plus Z2 plus ZF. IA0 and VA0 is 0. VA1 is EA minus IA1 Z1 and VA2 is minus IA2 Z2. We can substitute for IA1 and IA2 in those expressions and get the expressions for VA1 and VA. Further, it can also be observed that again in case of fault current, the fault current is nothing but equal to IB, and IB is IA0 plus alpha square IA1 plus alpha IA2. IA0 is 0. IA1 and IA2 are in opposite directions. So it is alpha square minus alpha IA1. And alpha square minus alpha is nothing but equal to minus j root 3 IA1. Therefore, the magnitude of the fault current is equal to root 3 times of IA1. And IA1 value is EA by Z1 plus Z2 plus ZF. Therefore, the fault current is dependent on the three impedances Z1 and Z2 and ZF, and Z0 is not appearing in the expression. It indicates that the unloaded generator, when an LL fault occurs at its terminals, then either it is through the fault impedance or not through the fault impedance, the fault current is totally independent of the zero sequence impedance. Now we will talk about the Draba line to ground fault on the unloaded generator. The circuit diagram for an LLG fault on an unloaded star connected alternator is as represented in the diagram below. Let us assume that the fault is taking place between the phases B and C. So now the phases B and C are shorted, double line, and is grounded, double line to ground fault. Therefore, the fault current is IB plus IC. Unloaded generator kept open, the fault current IA equal to 0. The neutral impedance is grounded through the impedance ZL. Okay. Now, from this diagram, we can write the terminal conditions. IA equal to 0. VB, VC will be equal to 0 because they are directly shorted and grounded. So, VB is also 0. VC is also 0. From the above terminal conditions, we can write the expressions for the symmetrical components of currents and voltages. VA0 is 1 by 3 times of VA plus VB plus VC, that is 1 by 3 times of VA. VA1 is 1 by 3 times of VA plus alpha VB plus alpha square VC, which is also 1 by 3 times of VA. And VA2 is also 1 by 3 times of VA. It indicates that VA0 is same as VA1 is same as VA2. That is, the zero sequence voltage is same as the positive sequence voltage is same as the negative sequence voltage. The current IA equal to 0. That is, IA0 plus IA1 plus IA2 equal to 0. Therefore, the above equations indicate that because the voltages of all the phase, this is positive sequence, negative sequence and zero sequence networks are the same, they are to be connected in parallel. So all the three networks, positive sequence network, negative sequence network and zero sequence network, are connected in parallel. Next, the following relations can be directly obtained from the figure. VA1 equal to VA2 equal to VA0, that is EA minus IA1 Z1, and the current IA1 is EA by Z1 in Z2 and Z2 and Z0 in parallel. Therefore, IA1 is EA by Z1 plus Z2 Z0 by Z2 plus Z0. And IA2 and IA0 can be obtained from the diagram by using the parallel currents theory of parallel distribution of the currents. So IA2 will be equal to the total current IA1 into the impedance of the other branch divided by the total impedance of the circuit. So IA2 is minus IA1 Z0 by Z2 plus Z0. Similarly, IA0 will be equal to minus IA1 Z2 by Z0 plus Z2. The fault current IF, which is equal to sum of IB and IC, is equal to, substitute for IB and IC, IA0 plus alpha square IA1 plus alpha IA2 plus IA0 plus alpha IA1 plus alpha square IA2. Substituting for the values of the symmetrical components of the currents, we get the fault current to be equal to 2 IA0 minus IA1 plus IA2. But it can be observed from the diagram that IA1 plus IA2 is nothing but equal to minus IA0. Substituting, we get IF to be equal to 3 times of IA0. Okay, and IA0 is given in the expression here. IA0 is equal to minus IA1 Z2 plus Z0. So substituting, the fault current equal to minus 3 IA1 Z2 by Z2 plus Z0. If the neutral is not grounded, if it is isolated, then Z0 becomes infinity. Therefore, the fault current will become equal to 0. So there is no fault current that is flowing when the neutral is not grounded. So it is inferred that the fault current in the system is 0 if the neutral is not grounded in case of LLG fault. Now let's look at the double line to ground fault occurring through a fault impedance ZF. Okay, so everything else remains the same, but B and C are shorted and they are grounded through ZF. Okay, so the expression slightly changes. VB is IB plus IC into ZF. VC is IB plus IC into ZF. IA continues to be 0. We can write the expressions for the positive, negative and zero sequence voltages. Thus VA1 is VA2, VA0 is minus VA2, VA0 minus VA2 is VB. So we get the expressions in terms of the fault currents. And the current condition IA equal to 0 indicates that IA0 plus IA1 plus IA2 is also equal to 0. So from these expressions we can write the circuit diagram. They suggest that all these three have to be connected in parallel such that between the negative sequence network and the zero sequence network, now we have the ZF coming into picture. Okay, between VA0 and VA2 we are having 3 times ZF coming into picture. The current that flows is IA0. Therefore, we have in between Z2 and Z0 3 ZF coming into picture through which the current IA0 flows. So from this diagram we can write the expression for the currents, voltages. IA1 is EA by Z1 plus this Z2 and Z0 in parallel. 3 ZF will come in series with Z0. Similarly, IA2 is the total current IA1 into the impedance of the other branch, that is Z0 plus 3 ZF divided by the total impedance Z2 plus 3 ZF plus Z0. IA0 will be equal to the total current IA1 into the opposite impedance divided by the total impedance Z0 plus Z2 plus 3 ZF. So in this case, the fault current is given by IB plus IC. So substituting for IB and IC in terms of the symmetrical components, we get the fault current as 2IA0 minus IA1 plus IA2. IA1 plus IA2 is nothing but equal to minus IA0. So substituting, we get IF to be equal to 3 times of IA0. Now finally substitute the value for IA0. So IF is minus 3 times IA1 Z2 by Z0 plus Z2 plus 3 ZF. So Z0 is present in the expression. So when the neutral is not grounded, Z0 becomes equal to infinity. Therefore, the current IF becomes equal to. This is about the different types of faults. That is double line to ground fault, the most severe fault, line to line fault, and the single line to ground fault occurring on the terminals of unloaded generator, which was earlier balanced and symmetrical in nature. What is the effect? All the three faults are discussed with and without fault impedances. And it is seen that in case of single line to ground fault, all the three networks will be connected in series. In the case of LL fault, the networks are connected such that the positive and the negative come in parallel to one another, whereas the zero sequence network is totally isolated. And in case of double line to ground fault, all three networks come in parallel to one another. Thank you.